Okay, everybody, now we are on section 6.2, or chapter 6, section 2, binomial distributions. So let's keep going. We only have 4 objectives here: determining whether a random variable is a binomial, determining the probability distribution of a binomial random variable, computing binomial probabilities, and computing the mean and variance of a binomial random variable. First, let's determine whether a random variable is a binomial. So let's take a look at your favorite fast food chain giving away a coupon with every meal. 20% of the coupons entitle you to a free hamburger, and the rest of them say, better luck next time. 10 of you ordered lunch at this restaurant. So suppose we want to know the probability that 3 of you would win a hamburger. In general, we let uppercase X be the number of people out of 10 that will win a free hamburger. What's the probability of the distribution X? In this section, we're going to learn that X has a distribution called a binomial distribution, which is one of the most useful probability distributions. So in the trial we just described, we call it, well, in the problem we just described, every time we do it, before we would say we would have different samples, and now we will call them trials. Okay, so when we're talking about binomial distribution, we talk about trials. So there are 10 trials. When a coupon is good for a free hamburger, we'll call it a success. If we don't get it, we actually call it a failure. The random variable X represents the number of successes in 10 trials. A random variable that represents the number of successes in a series of trials has a probability distribution called the binomial distribution. And binomial for a reason. You either have the result of success or the result of failure. So there's 2 things. Here are the conditions. First, you have to have a set number of trials conducted. We do. We have 10. There are 2 possible outcomes for each trial. One is labeled a success. The other one is labeled a failure. The probability of success is the same on each trial. The trials are independent, and that means that one trial doesn't affect the outcome of the other. And the random variable X represents the number of successes that occur. So the notation is N is the number of trials, P is the probability of a success. A fair coin is tossed 10 times. Let X be the number of times the coin lands heads. Is this a binomial experiment? Well, let's see. We've got our 10 trials. We have our success being heads. And we know the probability, if it's a fair coin, of getting a success for heads would be 1/2. So it looks like this may be a binomial experiment. Let's take a look. It is. Each toss is a trial. 2 possible outcomes, heads or tails. X represents the number of heads. Heads count as a success. The trials are independent because the outcome of one coin toss does not affect the outcome of the other. All right, now let's say we have 5 basketball players. All of you know I have basketball players by now that stay with me. And let X be the number of free throws made. Is this a binomial distribution? As soon as I read this, I thought, these 5 basketball players don't all have the same probability of making a free throw. So immediately I thought, no. And it's not. So the probability of making a success or making a shot differs from player to player, because they're not going to be equally skilled at making free throws. Although I think everybody should be able to make free throws because, after all, it's free points. 10 cards are in a box. 5 are red and 5 are green. 3 of the cards are drawn at random. Let X be the number of red cards drawn. Is this a binomial experiment? It's not. And here's why. The trials are not independent. They're showing you that you have 5 red, 5 green, 3 cards are drawn at random. Every time you pick a card, since we're not replacing the card, it's not an independent draw. So, no. Okay, determine the probability distribution of a binomial random variable. Here we go. Here we have a binomial experiment tossing 3 times a biased coin that has a probability of coming up 0.6 heads. Let x be the number of heads that come up. If we want to compute the probability of 2, so the probability of that exactly 2 of the tosses are heads, let's take a look at the 3 arrangements. Here we have heads, heads, tails, or heads, tails, heads, or tails, heads, heads. Now, the probability of getting heads, heads, tails is going to be the probability of heads being 60%, heads again, 60%, and if heads is 60%, then tails has to be 40%, or 0.6, 0.6, and 0.4. Remember, these two always add up to 1. So that would be 0.6 to the second power times 0.4. And this notation is going to become important because we're going to use it a lot for binomial distributions. Similarly, we can take a look at this one. Well, we know that if we have heads, tails, heads, or if we have tails, heads, heads, we also will get those. So now that we have probability of 2, which is heads, heads, tails, heads, or tails, heads, heads, we're going to take the 3 arrangements that we have, 3 times our binomial distribution, which is 0.6 to the second power and 0.4. So by the addition rule, examining this result, we see that the number 3 does represent the number of arrangements in the 2 successes and 1 failure in the trial. So in general, this number will be the number of arrangements of X successes in N trials, okay, which is the combination formula that we used before. It's the same formula. So the number 0.6 is the success of the probability, again having the exponent of 2 because we have 2 heads each time. And the number 0.4 is the failure of the probability. And again, this is 1 minus 0.6. They always add up to 1. And that's how we get the 0.4. So here's the scary looking formula. But if you look at it carefully, you'll see it's not so scary. For a binomial random variable, we have the combination. Now we know how to do this. We learned it before. Times the probability of successes, X number of times, and then 1 minus the probability, which will give you your failures. And then these two together will add up to give you your total number, N. Alright, let's look at compute probabilities, binomial probabilities by hand. Alright, here we have Pew Research Center recently reporting that 30% of internet users in the United States use the image sharing website Pinterest. Suppose that a simple random sample of 15 internet users is taken. Use the binomial distribution to find the following probabilities. A. Find the probability that exactly 4 of the sampled people use Pinterest. B. Find the probability that fewer than 3 of the people use Pinterest. C. Find the probability that more than 1 uses Pinterest. And D. Find the probability that the number of people who use Pinterest is between 1 and 4 inclusive. Alright, so here's A. We had 15. We know the probability of success is going to be 0.03. We want to find the probability that exactly 4 of the sample people use Pinterest. Here we go. Probability of exactly 4. We're going to take the combination. We have 15 total. We're looking at 4. Whatever this is going to be your successes. That's what we're looking for. 4 successes. 0.3 to the 4th. And then this is going to be 0.7. And then 15 minus 4. These two will always add up to n. Here's the combination formula from last chapter. So we have 15 factorial, 4 factorial, 15 minus 4 factorial. This stays the same, and we just simplified this. All right, so now we have this here, and you are definitely going to want to use a calculator for this. So you have 1,365 times 0.4 to the 4th times 0.7 to the 11th power, and we get 0 and 219 thousandths. Now let's look at the probability that fewer than 3 would use Pinterest. So here, fewer than 3 would be 0, 1, or 2. The possibilities that were fewer than 3 is a combination that none of them use it, 1 of them use it, 2 of them use it. So we have to do these separately. So we use the same combination formula as before. Then we take 0.3 to 0 power, which is just 1, and then 0.7 to the 15th. Then we're going to add that value. Do it again, having 1 being the number of successes. I'm going to go back a minute just to remind you. Here again is your combination formula. This is how many successes. This is how many failures. So in this one that we're looking at fewer than 3. So we're looking at a different number of successes. So that would mean either 2 successes, 1 success, or no success. So we have to find them all separately and then add them together. And we find that the probability is 127 thousandths. What about more than 1 person uses it? More than 1. Now, that seems like an awful lot of probabilities to add 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Or we could probably find the complement and subtract 0 and 1. Let's see what they do. Okay, so we're going to use the rule of complements. More than 1 is 1 or fewer, or 0 or 1. So we find the 1 or the 0 or 1. We do those probabilities separately. We add them together, and then we use the rule of complements. Take 1 minus that, and we'll get the probability of 0 and 965 thousandths. Now I want to reiterate again. I could add 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. One of the nice things about mathematics and mathematicians in general is like to find the easiest way to do it. So you can take the complement. Find the probability that the number of people who use Pinterest is between 1 and 4 inclusive. Well, inclusive means you're including 1 and 4. I usually say and including, but inclusive means the same thing. So we're looking at 1, 2, 3, or 4. So again, we find the combination separately, and then we're going to add all those values together, and we get a little over 1/2. Objective 3, we're going to look at computing the probabilities using tables. So here we have this same one with the 30 internet users. Find the probability of exactly 4, fewer than 3, more than 1, and 1 and 4 inclusive. Same problem we just looked at. Here, if you have these binomial tables, which either you can have them in a book, but now in these days of Google and the internet, you can just look it up on there and you're going to find your n value is 15. We want to know exactly 4, so we go here and then we're going to go straight across and we're going to meet up with our 0.3, and that's our answer right there. So really nice when you have the tables that you can just look it up that way. Now the next one, says fewer than 3 of the people. So fewer than 3, we're still at 15, and all of these have the number total here. And we have our 0.3, but we have fewer than 3, so we're going to take this one, this one, this one, 0, 1, and 2, and still add them together, and we get the same value of 0 and 128 thousandths. More than one person, again, I can take 0 and 1, get that value, use my complement rule, and there's my answer again. Between 1 and 4 inclusive, so that would be 1, 2, 3, and 4. And I'm going to look those values up for 1, 2, 3, and 4 and add them together and get 0.511 or 511 thousandths. We can also use our calculator to do these. So you'll see under there's a binomial PDF, binomial CDF. These commands are under the distribution menu, accessed by pressing second vars. So I'm going to go on here, show you if I hit second vars. Oh, gotta make sure it's on first. Let's turn it on. Clear. Second vars. Okay, here we have that. And that command is binomial PDF. Let's scroll down. There it is. Okay, and then binomial CDF. There it is. So those are the two that we would be looking for. The binomial PDF is used when finding the random variable when it's equal to a specific value. And the binomial CDF is used when finding the probability of the random variable that is less than or equal to a specific value. So those two things you'll have to keep in mind if you're using your calculator to find the binomial. Sorry about the glare that I'm getting. Okay. So, computing the probability of the random variable x equals x, the given values of parameters, and then p, you're going to use the binomial PDF command in this format. You'll put n, then your p value, then your x value. To compute the random variable of x is less than or equal to the value, again, this time, but you're going to use binomial CDF, n, p, and x. Here are the same examples we looked at before. So now we have n being 15, our probability being 0.3. Find the probability that exactly 4 of the sample people use Pinterest exactly. So we're going to use PDF. Here we put in our PDF 0.3 and our 4. And we get our value. Here we have fewer than 3. Fewer than 3. So here, fewer than 3 is going to be less than or equal to 2. So I can use my CDF command, 15, 0.3, and 2 to find my value. More than one person using Pinterest, more than one person, that would be 1 or fewer. So we're going to use the command for CDF to get our 1 value, because that'll take our 1 and our 0. And then when we get that answer, we're going to take 1 minus the answer to get our complement. What about 1 and 4 inclusive? Well, this one's a little bit different. So we can take our binomial CDF of 4, which will give us 4, 3, 2, 1, 0. But we can subtract from that the binomial PDF of exactly 0 because we don't include it in there. We only want 1, 2, 3, and 4. And if we take these two and subtract them, then we can get what's in between inclusive. All right, now we're going to take a look at computing the mean and the variance of the binomial random variable. Here we have the mean. We're going to take the value n times the probability. The variance is going to be n times the probability times its complement. And then the standard deviation, again, is simply the square root of the variance, which we knew as before. So we have a probability of a new car of a certain model will require repairs during the warranty period is 0.15 or 15%. A particular dealership sells 80 such cars. Let X be the number that will require repairs during the warranty period. Find the mean and the standard deviation of X. We have 80 trials with a success probability of 0.15. So the mean would be the 80 times that 0.15, and that would be 12. And then the standard deviation would be n times p, 1 minus p, take the square root of that, this is the variance on the inside. We will get 3.194, the square root. Oh, I think they should have ended that here. So it should be equal to 3.194. We should double check that. Let's double check that just to make sure. Okay, I'm going to go here. I'm going to take the square root. And I have 80 times 0.15 times, now I think we know if we take 1 minus 0.15, we get 0.85. And let's hit enter. Yep. Okay, so this square root bar should have ended right here. So the answer is 3.194. Make sure you note that in your PowerPoint, especially if you're printing it and taking notes. All right. Here's what you should know from today: how to determine whether a random variable is a binomial, the notation for the binomial experiment, how to determine the probability distribution of a binomial random variable, how to compute the binomial probabilities, and how to compute the mean and the variance of binomial random variable, and standard deviation, right? Okay, that is it for today. Last video for Monday, and the next video will be for Tuesday. See you then.